What if a giant asteroid was heading right towards Earth? What would we do? These questions come up a lot in pop science. They come up all the time in articles online, and this happens probably like twice a year. And I find myself explaining to my students that while there might be an asteroid that's kind of coming close, usually this means nothing. But the question comes up of, would we see one coming if it was dangerous? And could we stop it? In the movie Don't Look Up, scientists discover a deadly comet that's hurtling its way towards Earth. Now, they try to warn people, but people don't listen to the scientists in this movie, and it leads to disaster. This movie's mostly a satire on environmental disaster and things like that, but it also focuses on this real fear of potentially not being able to stop our imminent demise. This is a real fear because Earth has been hit before. You've probably heard before that about 66 million years ago, an asteroid that was some 10 kilometers across smashed into Earth and wiped out a lot of life. What it did is it caused fires and earthquakes and a massive cloud of smoke and debris in the atmosphere. And this debris, it caused kind of like an umbrella. This blocked out the sun, and this asteroid was one part of the puzzle that led to massive planetary temperature changes around this time. These changes eventually wiped out the dinosaurs. This is kind of what we're usually taught, right? So the dinosaurs were wiped away by this massive impact. Now, contemporary science seems to show that there was more going on than just that impact, but this type of impact could happen again. And that's why NASA did end up creating something called the Planetary Defense Coordination Office, or PDCO, the initials. Now, sounds like science fiction and is referenced in that movie, Don't Look Up, kind of as a joke, but it was really created in 2016 with one mission. It wanted to track. Its main mission here was to find, track, and study objects in space that could potentially pose a threat to Earth. These objects, we call them one thing. We leave them under this name called the Near-Earth Objects, NEOs. NEOs are comets or asteroids that come within 45 million kilometers of Earth. NEOs can be comets or asteroids, but the main defining factor of them is that they come within 45 million kilometers of Earth. This is a massive distance. This is 9 times the distance from Earth to the moon, but these objects aren't as massive, so these can be very small, and we're not as worried about those small ones, but we still want to understand them. But worse off is the ones that can actually destroy cities. Now, NASA's Planetary Defense Coordination Office works with telescopes and astronomers from all around the world. These include things like the Pan-STARRS Observatory in Hawaii, the NEOWISE Space Telescope, and the NEO Surveyor, the Near-Earth Object Surveyor, that will launch in 2027, if everything goes according to plan. Now, these telescopes and astronomers, the whole office here, they work together to try to look and scan the night sky every single night. And what they're doing is they're looking for anything that moves differently than what we expect. So stars and planets, we can predict that motion with high certainty. But if things are moving much faster, or in just oddly eccentric orbits, oval orbits, we want to map those, and we want to be able to find those. Those are the ones that we want to study because they might pose a threat. They could be coming towards us. If we don't know much about where it's going, we want to figure that out. Now, thousands and thousands of small objects enter our atmosphere every year. This is not a new thing. Some of these burn up like shooting stars, but NASA's obviously more worried about the big things, right? So tiny little things that we know are going to collide with us, we might study them, but we really care about the things that are over, say, 140 meters wide. This 140 meter range was come up with because simulations and all of our math tells us that this is the range that could really wipe out something in the size of New York or Tokyo. Now remember, this is nowhere near that 10 kilometer size that contributed to wiping out the dinosaurs, right? So this is much smaller than that, but we're still trying to keep track of all those things. As of right now, scientists have discovered roughly 32,000 near-Earth objects. Now, roughly 2,300 of these are what we call potentially dangerous asteroids. The rest, not as dangerous. We don't think they're going to collide with us. But even this 2,300 number, we really don't think any of these are on a collision course with Earth either. We still want to be monitoring them just in case. And these are the ones that you almost always hear about, right? Things like in the news the past 4 months or something, right? We heard about one recently. We heard about one middle of last year and the beginning of last year. So you hear about these pretty frequently, but we don't think any of these are actually on a collision course with Earth right now. Of course, our science and our understanding of their motion and what's out there is changing all the time. We're studying, we're analyzing, we're finding new stuff out so frequently. But right now, we think we're pretty safe. But the time might come when we find one and we realize we might not be safe. So the question comes up of, can we actually stop one of these massive asteroids, one of these ones that could destroy something like a city or worse? Well, all the news a few years ago was telling us that maybe we can. Maybe we have a chance to stop these. This is in 2022. NASA tested something huge. Now, this mission was all over the news, and you might have heard of it. It's called DART. It stood for Double Asteroid Redirection Test. What NASA did is they launched a spacecraft, something that was roughly between the size of a mini fridge and a real fridge, and their goal was to crash it into a small asteroid's moon called Dimorphos. That's right, this asteroid had a moon. Now, this is a small asteroid moon that circles around another asteroid, and these orbit roughly 11 million kilometers from Earth. It's not that this asteroid posed a threat to us. We were just testing this to see if we could deflect something that did pose a threat. Now, why'd we pick this? Well, we wanted to see if hitting the moon of this asteroid would change how it orbits that asteroid. So really all we did is what we call kinetic impact. We smashed this spacecraft into the side of this asteroid moon at a very fast speed to see if it affected the motion of that moon. And what it did is it slowed the asteroid enough to actually impact its orbit around its asteroid. And what it did is it collided with the asteroid's moon, and it slowed it down just enough to change its orbit. And this is huge. This is exactly what we were aiming for. This is the first time in human history that we were able to change the motion of something orbiting in space. And ultimately, it proved that asteroid deflection like this is possible. It might take a lot of number crunching, and we probably want a pretty good radius, and we probably want a pretty good idea of when it might hit us, but this proved that it might be possible. And that's one big method. It's really the best thing that we've tested so far. Again, this is our kinetic impact. Whether this is through DART or something else, this proves to be a potential option. But it's not the only thing that people have bounced around. Some of the others include things like gravity tractors. A gravity tractor sounds funny, but really what it does, similar to DART, we send a spacecraft, it goes flying by the thing that we want to shoot it at, just enough that we think it might actually change its orbit. The gravity of these two objects could impact how the orbit moves. Another method that we have thought about and is a potential option, but again, DART has the best chance so far, but this is laser ablation. Laser ablation aims a laser, a really strong laser, at an asteroid so that we can vaporize some of its surface to try to change its orbit. So these are three really good options we have. Kinetic impact, and this has been proved with DART. We have gravity tractors, and we have laser ablation. Now, the last resort, and you might have seen this in something like Armageddon, the movie or something, is of course nuclear weapons. This is kind of a last resort. People have suggested that it could be possible to break or deflect an asteroid by hitting it with nuclear weapons. This is obviously controversial and dangerous, but to tell you the whole picture, that is part of the discussion that comes in when we're talking about asteroid deflection. So what would this actually look like, right? If we actually found one that would be dangerous, what would this look like, and how would it compare to things that you've seen on the news in the past few years? Well, realistically, it would hit the news. People would hear about it, NASA would alert the public, or whatever agency finds it, would alert the public and collaborate with world leaders and other agencies to share data and get more data on it as fast as possible. This means we might point, depending on how serious it could be, we might point most of our telescopes there to try to see if we can learn more about it. And all this data, of course, builds into the next big step here, right? So step one is alerting people and collaborating. Step two, with all that data, we want to try to calculate its orbit and the risk posed by it. This would be a quick time where we need quick turnaround to make models that predict how this thing moves. And lastly, this leads into our third step here, right? And this is actually enacting some type of asteroid deflection system. Realistically, we need time for this. We probably need years right now. But if we find something and we have that time, our goal is to send a spacecraft up and change its orbit, whether that's through gravity tractoring or kinetic impact. These are our options. And of course, the problem is that we do need that time, right? If there's not time for that, what do we do? And realistically, I think the best option is evacuate and disaster plan, right? I mean, if we know that this thing's gonna hit us, we want to model where it's going to hit. We want to understand where the impact could happen so we can better model what that impact will look like. And if we know the risk that's posed to people, we can best serve those people, right? We can evacuate people from dangerous areas. We can provide disaster support to surrounding areas. And this is really why stuff like this is so important, right? It's easy to look at science research and space research and say, oh, why would we need this, right? But the reality is, the better funding and research we have into planetary defense, the better chance we have once we've actually detected something to save lives, right? This would be millions and hundreds of millions of lives that we could change. So pouring funding into these ideas is really important, not for space science, but for people, right? Now, I'm not trying to scare people, right? The idea of this stuff, what I'm really trying to say is that you hear about this stuff all the time in the news. And chances are those are not actually dangerous asteroids. Often what happens is we find an asteroid and we say, oh, this might be dangerous. We start that first piece, right? That collaboration piece. People get more data on it. They understand more about it and its orbit. And they say, okay, it's actually not dangerous. So sometimes we get red flags or false alarms in the news. But realistically, the chance of one hitting Earth in our lifetime is not zero. It's small, but not zero. And this is really why things like Armageddon and Don't Look Up, while those are science fiction, planetary defense at its core is non-fiction. This is stuff that needs to be happening. We need to understand what the risks are about these things out in space. And this affects everyone, right? While it might sound like a movie plot here, right? In reality, it's a global responsibility. It's for us people to come together to fund the science that matters and to save lives. Now, I encourage you guys to look more into this stuff because this is stuff that we've researched a little bit to tell you guys about, but we want to hear what you guys know too. So let us know more in the comments what you guys know about and have researched. We'll leave some links in the description of research we used for this video. If you want to keep up with science and science information like this, make sure that you're subscribing, you're liking this video, sharing with people, and check out other videos that we have to learn more.